At the heart of WBPP is the calibration of data, which is what this script was specifically designed to handle. It takes the tedium out of the task. Just simply load and configure the settings, and all's going to go well. This section highlights the basic concepts of calibration data and how it works in WBPP. I've made a graphical representation of the parts and the steps that are in play. For those that are just starting in astronomical image processing, this section will definitely jumpstart your understanding of what is often a very difficult first hurdle. So let's go. I want to talk about flat darks and dark frame optimization, and of course, ultimately, properly calibrated files. All of this is just ahead. Let's start with the simplest of these calibration files, which is a bias frame. Now, when you turn your camera on, you plug it in and you energize the sensor. There is a voltage. There's a certain amount of electrical activity that's occurring there. So if you take the shortest possible exposure, 0 seconds if possible, and you download the information, you're going to see there are values. There is stuff going on there. In order to characterize this level of activity, you take many of these frames, these bias frames, and combine them. Just so you know, camera manufacturers often set that voltage level. So that average level that you're going to record when you take a bias frame, there is no particular right or wrong number. You would expect it to be relatively small, but it could be on the order of hundreds or even a few thousand counts. It just depends from camera to camera. So you take these multiple frames and combine them. In PixInsight, you're using the process of image integration to combine them and then create a master bias. Of course, now you're not going to do that. This will be done for you internally by WBPP. And I am showing you a picture of a master bias frame that comes from a camera that I use. And I just want to point out a couple of things. You already know that the value itself can vary from sensor to sensor. In addition, there's structure. You'll often see, and this has a lot of structure, all kinds of vertical banding going on here. And you'll notice that it's not equally bright across the field as well. It's a bit brighter in the middle than it is towards the edges. All of this is perfectly normal and just perfectly fine. So don't get freaked out when you look at your bias if you haven't looked at one closely before. This is very typical. Now, a dark frame is a natural extension of a bias frame. Again, the shutter is going to be closed, no light is hitting the chip. The chip is being held at some temperature. So that's important to say, especially when we're talking now about dark frames, because of what I'm going to show is the characteristic of how they work. So if you take that really short exposure and call it a dark frame, maybe instead of it being 0 seconds, now we're talking about a 1 second exposure, or even a 5 second exposure, you still, if you look at that frame, it still might look like a bias frame. You won't see any difference. In fact, if you were to subtract maybe these two frames, you wouldn't see a difference. It's only until you start doing longer and longer exposures that you would start to notice some differences, especially if you literally subtracted one image from another. You would notice that you would be left over with some extra stuff. This extra signal, what it comes from, as you do longer and longer exposures, I'm representing it here by the blue bits here, is there's a thermal activity in the bulk of the chip. So the atoms, silicon atoms, if you will, in the chip are always being jostled at some temperature. And that jostling, that vibration, elevates some electrons to the conduction band, where they move around and then they get captured in these little potential wells, which are your pixels, which you download. So through time, you are accumulating, effectively, electrons, and it is just for this kind of thermal reason. The nice thing about that process, is it is straightforward. It is predictable. It is something that you can say that in twice the exposure time, you would expect to have twice the number of electrons. Now, the rate itself of how fast this gathers, that does change from sensor to sensor. That can be different from sensor to sensor, but it does change linearly for well-behaved sensors. So for the moment, I'm just going to be talking about sensors and cameras that act in a way that is predictable. So now I'll show you that this is a predictable idea. And the special name for this extra voltage, these extra electrons that you gather through time, it's called the dark current. So a dark frame, when it's long enough, is actually comprised of the bias level plus this extra stuff. And so throughout this demonstration, I'm going to refer to a dark frame as being the combination of the green box, which is the bias level, plus this extra stuff. But the most interesting part of well-behaved cameras, of predictable cameras, is that for short enough exposures, that dark frame is indistinguishable from a bias frame because there isn't either enough, there isn't any, or there isn't a significant amount of the dark current, of those extra electrons. And you'll find that there is a benefit to, you can take advantage of that fact in terms of calibration of data later on. But just understand again, the dark current is what really defines a dark frame in the sense of this predictable and well-behaved kind of sensor. Like we did a moment ago, we're going to take these individual raw dark frames and combine them to create a master dark. Now again, this is all done in WBPP. It's doing the image integration for us. So if we bring raw frames to WBPP for whatever exposure time it is, we might have different darks, so we'll have different groups of raw data. On the fly, WBPP for each of those groups of our darks will create a master dark of each group. So it's doing this for us. And again, over here, I'm just communicating that when you do that combining, it's almost like you've made a master bias with this additional, what I label here the dark current, these additional electrons. So looking down at the bottom, now we can do a direct comparison. I have a master bias on the left and a master dark on the right. So the master bias is a 0-second exposure. The master dark in this case is a 10-minute exposure. I think you would be hard-pressed to see the difference between the two. Maybe you can tell there's a little bit of a glow up here in the top left. But other than that, just initially at first glance, they look very similar. That actually communicates something. They both look like a bias frame, which means that this, whatever these extra electrons are, it must be a very small thing compared to the bias level. And that is true. For most cameras, for most sensors that are cooled, the colder you make the sensor, the less of this electrical activity you get. That rate can be very, very small. And I'm just going to say a rate, and I really don't know how accurate this is, but it might be for some cameras on the order of 1 electron you might detect every second, or maybe every couple of seconds. The colder you make the chip, the less of that dark current you'll see. And it's a very small value compared to the bias, which can be, like I said, thousands of counts. If we do zoom in, though, you can start to see one major distinction between a bias frame and a dark frame. You still see kind of that bias level, but we also now see lots of bright little pixels. So there's a population of pixels, certain pixels that just gather those electrons, that charge, faster or in a different way than their neighbors do. Now, it's not all the pixels, but there's a certain population of them. So those are going to do the same thing every time, but they are just different than their neighbors. And when we calibrate our data, the same thing is happening in all of our other frames, so it will calibrate out. The last calibration type is a flat field image. Now, flats really are different than biases and darks because now we have the shutter open, light is coming into the sensor. And the reason we take this kind of calibration is to measure how non-uniform the chip or the sensor may be illuminated due to the optical characteristics of our system. That's one reason. There's another reason, especially if you're making measurements with your camera. It is to measure the pixel-to-pixel response to light. The sensitivity of those pixels can vary from pixel to pixel. So that's what you need for doing science. So flat field images then characterize our sensor to allow us to get rid of the vignetting and to normalize the response of the pixels and do really nice things. Flats are usually very short, because you can usually either have plenty of light or control the amount of light that you're illuminating the chip with. And so you don't expect for a flat field image to have any of this dark current. A flat then is just going to be the light plus the bias level. What's not being communicated here is the fact that, it looks like the bias level is equal to the degree in which the flat has some signal. And that is not true, of course. When you take flats, they have a lot of light. And so the number of counts, the amount of signal there compared to the bias is much, much larger. But I am just trying to indicate that we have some bias level without, for short exposures, without very much or any dark current. And that's all that comprises the flat. It's just the light and the bias. So if you want to do the steps of calibrating the flat, then you take the master bias and you subtract off that bias amount, and then that leaves you with raw flats that are bias subtracted. And these raw flats that are bias subtracted are, of course, can be integrated together to create the master flat. And you'll notice, of course, I'm leaving these little empty spots to communicate that the bias has been subtracted, but it's just a reminder that the master flat is a calibrated creature. So that's just something to remember. Now, depending upon the kind of imaging that you're doing, if you're using a monochrome camera, you might have many different groups of flats that are calibrated and then combined to create different masters, because you'll have it for each filter. For one-shot color camera sensors, then you might just have a single set of flats to calibrate the data that you're working with. Now, a couple of things about what happens in WBPP is that when we create these bias subtracted flats here, what happens is that these files are calibrated, because this is a light frame like just any other light frame. So these files are saved. So you can find in directories that you'll see later on here that I'll explain, they are saved as calibrated flats. Now, if you wanted to go back and integrate them on your own to do this last step with them, I guess you could. So you will see the calibrated flats as well as the master saved in another directory, which is the masters directory. But the important thing is that this master flat, this is the actionable part once it has been integrated, and we're now looking at a calibrated master flat. That's what we apply, of course, to images, which you'll see in just a moment. And it is a perfectly acceptable thing to do this subtraction of a master bias to create these bias subtracted raw flats, which are integrated. But I need to add something really quickly here, which is that, again, this works when the exposures are short. So I've put a time here of less than 30 seconds. It might be that you need to take exposures for your flats that are longer than 30 seconds. Perhaps if you're using a narrowband filter or something like that, and you're exposing for 30 seconds, a minute or more, then what you end up with perhaps is a flat that does have not only the bias, but a little bit of that dark current is showing up there. So at that point, what you need to do is subtract an actual dark that matches this situation. So this is the bias plus that extra dark current, which is a dark frame, but it is often called a special thing because it is used specifically to calibrate flats. So it's called a flat dark. Now, it is a dark frame. It is nothing more than just a dark frame. We put it in the darks column in the darks panel, but it's often called a flat dark because we know the purpose of that particular dark frame is to calibrate the flats. And I guess that's contrasted with the idea of taking a dark frame that would calibrate other light frames, not just flat field images. So it's a dark frame, often called a flat dark. Now, everything I've described here works with cameras that are predictable in nature, the ones that are well behaved. One of the nice things about this ability to do this with a master bias is it's one of two ways we use a master bias to take advantage of this predictability, of this well-behaved nature of these particular sensors. But shortly enough, I'll be talking about sensors that unfortunately don't have this characteristic, and then you just need to do perfect matching every time. You can't take advantage of the benefit of the bias. Before we leave this screen, I just want to say one more thing that I think is important to spell out, which is that you might wonder, well, if I have a particular exposure time for my flat, when do I start to care that there might be some dark current showing up? And the answer is, I can't tell you, because it depends on sensors. Actually, CMOS sensors, as it so happens, tend to collect this dark current a little more quickly, accumulate these electrons more quickly than a CCD camera of kind of a similar nature. But that's not so critical. Really, the way to think about this is that if you don't know, or better yet, if you want to find out, my recommendation for everyone is to begin by using master flat darks, or use flat darks to calibrate your flats. And the reason I say that is because in this way, you can't go wrong. If you happen to take, let's say your flat is at an exposure of 20 seconds, and you might wonder, is it a dark current? Well, if you take a 20-second exposure of a flat, and then you have a 20-second dark exposure, but it actually doesn't have any dark current in it, there's no harm done. You can still put it in the darks column, being oblivious to the fact that it doesn't have any dark current in it, and you just subtract it as normal. These two operations are identical. It is literally just a subtraction, so it actually doesn't matter which column you put it in, except that, of course, bias frames are used for other purposes, so it is somewhat important that we get it right. But the point is this mathematical operation is the same. So if you take a 20-second exposure and you don't know that there's dark current, you can just still put it in the darks column. Call it a flat dark. So my suggestion is for everyone, take flat darks, match your darks for flats until you have determined, maybe the exposure time or whatever it is, to know that, well, gosh, I'm not detecting any dark current up until this point because my flats are calibrating correctly and there's just no problem, so I can get away with using biases. But don't start with using a bias first. Start with the flat darks first so that you know you're getting reproducible results, and then you can experiment with using a bias to understand where that line is, if it exists at all, which again, I am foreshadowing something that I'll be explaining in a moment about cameras that unfortunately do not behave, and so it's more difficult to, it's just you can't do it. You have to match all the time. And since I just talked about the calibration of flats, flats are a light frame. I mean, the fact that we're looking at a panel or the twilight sky doesn't matter when we look at a galaxy or a nebula. It's the same thing is happening where light is illuminating the chip, and depending upon the length of the exposure, we are going to have that bias level, of course, every time. And then we're going to be gathering our electrons in our dark current. So we have the frames here that are necessary to do the job to calibrate a raw light frame. And this is what you would expect. If we have a master dark, we're going to take that matching master dark. It has the same exposure time. It'll have the same configuration in terms of binning. It'll have the same temperature. Everything will be the same. So that means that the bias level and the dark current will be the same. We subtract that from our raw light frame, and we end up with just the signal. Of course, you'll notice here that our signal is it's not a nicely illuminated field. When we take a picture of the galaxy, we still have this problem of taking care of or compensating for that non-uniformity in illumination. Well, that requires the other bit that we also have in hand, which is our master flat. So here on the left, we do the initial calibration of removing that electronic signature, which is the dark current and the bias level. Remove that. And then we apply the master flat. And the operation is, it's not subtraction, by the way, it is division. You actually divide your signal here by the master flat, and then you multiply times a scaling factor to calibrate that frame to compensate for that non-uniformity and response of those pixels. And then you get, finally, what we've been searching to get, which is our calibrated light frame. And this is actually where we wanted to end, in the sense that we're going to take the groups of these calibrated light frames and combine those to create our ultimately our integrated image. However, what I am stressing in this, of course, tutorial of WBPP is the idea of just making sure that all of the pre-processing part, the calibration part, that's the main part. You can use WBPP to go a few steps more, to do a little more work for you. But what I'm highlighting here is the calibration process. So this calibrated light frame, and many of them that are outputted, that really is, as far as I'm concerned, that's the end result that we really are looking to get.